Okay, welcome back. This is going to be a video for advanced math. I know I've only put one half of one section's video up for this course so far. I apologize for that. We'll try to get this one done and then do maybe 4-2 either today or tomorrow as well. If you remember 4-1, we were talking about the concept of an exponential function, and we remember that an exponential function is structured like this: f of x equals a times b to the x. A is our coefficient, b is our base, and then x in this case is our exponent. A can be 1, that's fine. If if the one that we did last time, I think we looked at y equals 2 to the x, and there, a is 1, and b is 2, and then our exponent is x. Well, part of what you're going to have to do in the assignment is to graph some exponential functions applying the transformation rules. Okay, the same transformation rules that we talked about during graphing trigonometric functions, the same transformation rules that we talked about maybe during conic sections as well. If I have y equals a times b to the x, I can do several things. I'm going to say most of them. For one thing, I can stretch this curve vertically by changing the value of a. Okay, if a is a number greater than 1, that will stretch the curve vertically. If a is a number less than 1, it will compress the curve vertically. If a is negative, okay, if a is negative, that will reflect the curve across the x-axis. So just for example, if I had the function f of x equals, let's say, negative 3 times 4 to the x. Well, the parent graph of that function would be 4 to the x. Okay, and you can figure out what that looks like pretty easily just by applying a few points. And then the negative 3 in front of it does several things. Number one, since the absolute value of negative 3 is greater than 1, the curve will be stretched vertically. And then the fact that a is negative, right, will reflect that entire curve across the x-axis. So that's what that would do. Now, in addition to reflecting and stretching vertically, we can also translate an exponential function up, down, left, right. Just for example, if I had y equals, let's do just 2 to the x minus 1. Okay, so now my exponent, there's been a minus 1 added to the x there at the end of the exponent there. And if you remember, if you subtract a number from the variable, right, that's going to shift the entire curve to the right. Okay, so the parent graph here would be y equals 2 to the x, and that entire curve would be moved to the right 1 unit. Now, if I want to shift that same curve up or down, I can add or subtract a number here at the end. If I put a plus 3 at the end, that's going to shift the entire curve up 3. So this time, the parent graph's still 2 to the x. That minus 1 makes the entire graph go to the right 1 unit, and then that plus 3 at the end makes the entire graph go up 3. Teddy, we doing okay? Still?
4 minutes.
Okay, excellent. Okay, and like it's suggested on the problems in the assignment, they suggest that you use a graphing calculator to help you with this. And if I haven't said it to this class yet, I don't remember if I did or not. If you don't have a TI-84 at home, TI is making the software available for free to anybody. Go to the TI website, Texas Instruments, and you'll be able to download something to your device or your computer that will emulate a TI-84 and do things just like that. Or of course you can use Desmos as well, just on any device at all. All right, let's talk about the asymptote for a minute of an exponential function. So an exponential function will have an asymptote, and the function we graphed last time, y equals 2 to the x, if you remember, it looked something like that. And if you remember, as I come to the left here, as I go toward negative infinity, that curve is going to approach the x-axis forever, never cross or touch that x-axis. So we would say that this has a horizontal asymptote, and the equation of the horizontal asymptote, remember any horizontal line, the equation is y equals a number. In this case, it would be y equals 0. Okay, y equals 0 is the horizontal asymptote for that graph. Now, if I change that to y equals, say, 2 to the x minus 3, and we push the entire graph down 3 units, the new horizontal asymptote would be the line y equals negative 3. Okay. If you ever you can't figure out where the asymptote is, just graph it on a graphing calculator. You'll figure it out pretty quickly. All right, now let us talk about an application. The application that you'll see in this section has to do with compound interest. All right, now the compound, now first of all, what is compound interest? Well, compound interest is the concept of, I'll explain it here. So if you have a savings account that pays interest compounded daily, okay, my savings account or my checking account, it's actually not a savings account, it's a checking account, but our main checking account pays interest that's compounded daily. All right, now how is that better than just paying simple annual interest? Well, if you have $1,000 in your savings account or checking account, if it pays interest, if it just pays, say, 2% annually, the bank's going to wait till the end of the year, and then it's going to put $20 in your account. Okay, 2% of $1,000 is $20. So over the year, you earn $20 worth of interest. Well, if it's compounded daily, what the bank's going to do is it's going to put 165th of your interest in the first day. And then it's going to, the next day, it's going to, so you'll have a little bit more in your bank account after even one day. Then the second day, okay, it's going to put another bit of interest in there. It's going to put in interest earned on your new balance from day one. Okay, let's, I tell you what, we'll just put some numbers with it. I am going to grab my calculator here. It's right over here. If I put $1,000 into a savings account that earns 2% interest compounded daily, I'm going to calculate really quickly how much I'd earn the first day. It's not going to be much. Okay, let's see, times 0.02 divided by 365. Okay, it looks like I'd earn about 5.5 cents the first day. So then I'd have $1,000 plus 5 cents or so in there the second day, and they figured the interest for the next day. They pay you interest on $1,000.05. Okay, so you're earning interest on a bit more money after that second day. Okay, and there's a formula, of course, for compound interest. You've probably seen it somewhere before, I hope. P equals P naught plus R over N T. Okay. So we'll talk about what each one of these symbols represents. This is your final value. This is your initial value. R is your annual interest rate written as a decimal. Okay, so this is your interest rate. Or if you've got some other sort of investment vehicle, it's your rate of return is what it is. And be sure to write that as a decimal. So if you're earning 5% interest, you're going to write that as 0.05. N is the number of periods per year. So if your interest is compounded daily, N would be 365 because there are 365 days in a year. If your interest is compounded monthly, that's 12 periods per year. If your interest is compounded quarterly, that means 4 times a year, so 4 periods per year. And then T, this N is the same as this N down here. And then T is your number of years. So that's time in years. Okay, so that's the formula for compound interest. Let's take it out for a test drive here. So I'm looking at, this is actually problem 22 out of your assignment. It says 1,200, at least on my side, it says $1,200 is invested at an interest rate of 6.75% per year compounded quarterly. Find the value of the investment after, and then it has several different number of years. I'm going to pick the last one, which is 12 years. Okay, so the final amount is going to be your initial amount, which we said is $1,200. It said that the interest rate is 6.75%, so I'm going to do 1 plus, and then here's the interest rate, 0.0675, divided by the number of periods per year, and goes in the denominator there. So compound quarterly means there are going to be 4 periods per year. And up in the exponent, we put the time in years, so 12 years, and then also times n, which is 4. So I'm going to put 4 times 12 right up there. Okay, now if you do that, this should just be a calculator entry, so you can play along at home. I'm going to enter that right now. It's just one calculator entry, really, if you do it correctly. 1 plus 0.675 divided by 4. Now, the one thing you have to be careful of, and I'm getting ready to type in my exponent, if your calculator's in classic mode, which I greatly prefer, and it doesn't show the exponent up as a little exponent, it shows a caret key and then the thing, you have to keep that in parentheses. You have to keep the 4 times 12 in parentheses, or you could just, if you know what 4 times 12 is, you can just type in 48. I just did this and I got $2,679.32. Okay, so you started with $1,200, and after 12 years, it's become this much. Okay, that's great. That's not terribly impressive. I wonder what it would be if we compounded that daily. All I have to do is change that to a 365 and that to a 365. I can fix it on my calculator entry very easily. I'm just going to go down and put a 365 in the denominator there, and up here in the exponent I put 12 times 365. Now, you will notice that I don't make a lot more. If I compound the interest daily, it's $26.97 and 29 cents. So about, what is that, $18 more approximately. Now, $18 is nothing to sneeze at, I suppose. But after 12 years of having your money tied up, it's not that much. Now, you can compound it more often than just daily, but you don't gain much extra. Okay, once you get past about monthly, you're not gaining that much. You can compound it every second. You can compound it every millisecond. And in fact, you can compound it on an infinitely small period of time, and that's called continuously compounded interest, which isn't in this section, but it is in this chapter. Teddy, how are we doing on time here, boy?
14 minutes.
Okay, yeah, we better sign off. This should be good for you to get through 4-1. Have a great day, stay safe.